Alright, so let's continue with diagonalizability. So last time we saw that uh, some A is diagonalizable if and only if it has n linearly independent eigenvectors, where A is a n by n matrix. Let's say so. So when do we have n linearly independent eigenvectors? So this is our interest, right? So when we have this, then it is same as saying that it will be diagonalizable, right? So what we need, we are looking for a necessary condition, or you could say, I'm sorry, we are looking for a sufficient condition. Okay, we are looking for a sufficient condition, right? What does that mean? That means we are looking for a condition, say some condition, okay, some condition that should imply diagonalizable right? So this is what a sufficient condition means. So let's so let me state theorem. Theorem states that uh, so let lambda 1 up to lambda k, say k, call it lambda k, be distinct eigenvalues of a matrix, say A, in M and C or M around, whatever, right? Then the set V1, V2 up to Vk is linearly independent, right? What is V1, V2, Vk? Where Vi is an eigenvector corresponding to lambda I. Okay. So in fact, this sometimes we also refer to lambda I comma Vi as an eigenpair, okay, which is a pair of eigenvalue and its corresponding eigenvector. So what it is saying that we have to show linear independence, right? So let's look at the proof. So assume otherwise. So suppose that this set V1, V2 up to Vk is linearly dependent. Suppose. What does that mean? That means see what it means that out of these vectors V1, V2, Vk, some of them will be linearly independent, right? So some of them, right? Some of them will be linearly independent. What I mean to say is that every linearly dependent subset, or sorry, every linearly dependent set will have a linearly independent subset, right? And let's call that some of them, say for example v1, suppose say for example v1 up to vm, right? Suppose these are linearly independent, right? And let's say Vm plus 1 is in the span of V1 comma V2 up to Vm. Hope this is fine. This is nothing but this entire statement follows from the fact that V1 V2 up to Vk is linearly dependent. Okay. So there exists such an M. Okay, there exists such an M for which V1 V2 Vm is linearly independent, and the next one would be in the span, making it linearly dependent. But what does this mean? This means that Vm plus 1 can be written as C1 V1 up to Cm Vm, right? Now what we do, we multiply the entire thing by lambda m plus 1. Lambda m plus 1 equals C1 lambda m plus 1 times V1 and so on, Cm lambda m plus 1 Vm. Okay. Right. This is on one hand. So let's call this equation, say, star. So this is obtained by multiplying star with lambda m plus 1. Now what we do, I multiply star with the matrix A. Okay. Then what would happen? I would have A times V m plus 1 equals C1 A V1 up to Cm A Vm. But then on the left hand side, A times Vm plus 1 is nothing but lambda Vm plus 1. Sorry. Lambda m plus 1 Vm plus 1, right? And on the right hand side we have C1 lambda 1 V1 up to Cm lambda m Vm. Right? Call this equation double star and call this one triple star. Now compare double star and triple star. What do you get? We obtain that. Observe carefully. C1 times lambda 1 minus lambda m plus 1 into V1 plus C2 times lambda 1 minus lambda 2 minus lambda m plus 1 V2 and so on, right? And so on up to what? Up to Cm times lambda m minus lambda m plus 1 times Vm equals to 0. What does that mean? But observe that Ci's are not all 0, right? Because if Ci's are all 0, then Vm plus 1 would be 0, right? So here I should write not all Ci's are 0. Okay. So not all Ci's are 0, right? And each of them is non-zero, right? Because lambda 1 is different from lambda m plus 1, right? In fact, lambda 2 is also, all of them, right? All of them are different. So this is non-zero, this is non-zero. So right? All of these terms are non-zero. Right? So what does that mean? So this kind of a combination implies that V1, V2 up to Vm is linearly dependent, which is a contradiction. Why it is a contradiction? Because observe that we have assumed in the beginning that uh, some of them will be linearly independent, and that is this set. Right? So we have taken them to be linearly independent, and then we got this contradiction. What does that mean? That means our initial assumption is wrong, which means this set should be linearly independent. Must be linearly independent. The proof is clear. Another important property I like to note down is that, so let's say, so this can be treated as a corollary. So let's say suppose that alpha 1, sorry, lambda 1, lambda 2, lambda k are k distinct eigenvalues, suppose. Suppose of what? Of A, where A is an element of M and C. Right. Now, additionally, let the dimension of the null space of A minus lambda I be equal to, say, n suffix I. Right. This is nothing but the nullity of A minus lambda I. Right. This also means this is the number of linearly independent eigenvectors. Okay, so number of linearly independent eigenvectors corresponding to the eigenvalue lambda I. Okay. So the theorem says then A has I running from 1 to k and I many linearly independent eigenvectors. Right. So this is the claim. Let's look at the proof. So how would you go about proving this? So corresponding to a particular lambda I, right? Lambda I. So suppose lambda I corresponds to the eigenvectors, say ui1, comma ui2, right, and so on, ui n suffix I, right. Suppose these are the eigenvectors corresponding to lambda I. Okay, suppose. What we need to show? We need to show that so let's call this set Si. What we need to show is that we need to show the union of all Si, right? I running from 1 to k, this set is linearly independent. This is what we need to show, right? See, how many elements will this set have? So, union summation I, Si, this cardinality would be equal to summation Ni, right? So we need to show that this set is linearly independent. Now let's take a denotation. Okay, let's say let Pj of A, right, be a polynomial of J such that take the product of all A minus lambda I. Take the product of all of them, right? These are all, so take it from lambda running from 1 to k, but don't take the one where I is equal to j. So you're only taking for those I which is not equal to j, right? Right? Then, so what will Pja be? Pja will also be a matrix in MNC, right? Now, what will be? Suppose you multiply Pja with some vector u. What will you get? You would get 0 if u is in the kernel of A minus lambda I, right? For some I not equal to j, right? Is this clear? Why? Because if I is not equal to j, then and if u is in the kernel of some of them, then that term in the product will become 0, right? It's okay. Hope this is okay. Now, what if, so this is one case. What if u is in the kernel of A minus lambda ji? Then what can we say? Then this would be nothing but the product of all lambda j minus lambda I, right, where I is not equal to 0, times the vector u. Let me denote the vector u like this, times the vector u. So just verify that this function is correctly written. Okay. Now what we need to show? We need to show that the union of Si is linearly independent. So what are the elements in union Si? You have u11, right, u12, so on, right, up to you have k1, uk2, so on, uk n suffix k, right? So this is the union of all Si's. Right. Now consider C11 U11 plus C12 U12 and so on. Ck n suffix k uk n suffix k equal to 0. Suppose this is equal to 0, right? Now if you multiply the equation on the left by Pja, right? So now you apply, so now multiply on the left by Pja, then for every I plus I not equal to j, there will be nothing. Okay, all of them will vanish. So what would you get? You would get only those terms for which you have j in the first coordinate, that is cj1 uj1 plus cj2 uj2 and so on. cjnj ujnj. Okay, so this will remain, right? Along with what? Along with that, you will get lambda j minus lambda I product j not equal to I. So this will be equal to 0. But then all of the eigenvalues are distinct, so this can never be 0. Right? What does that mean? That means that Cji j1 uj1 up to Cjnj ujnj, this is equal to 0. But what we can say, but what is this? So we know that, but this set uj1 up to ujnj, this set is a basis of the kernel of a minus lambda j I. What does that mean? That means they are linearly independent. That means that Cj1 equals Cj2, all of them, Cjnj, all of them are 0. Right? Right. So what did we do? We started with an arbitrary combination of these vectors being equal to 0, and then we showed that all of them should be 0. See, the others are already 0. Okay. So this is another corollary. So what we have seen is that if you have, say, n distinct eigenvalues, that implies that the matrix is diagonalizable. The converse is not true. The converse is not true. Why not? Take say for example I2. This is diagonalizable, but so this is diagonalizable, but no time, but not possible, but doesn't have. Okay, so I'll just write, but no distinct eigenvalues. Right.